Oh, that was a little bit too much drama there. I hope things will be okay. It's really... What?
Yeah, if you could turn off the phone.
Oh, I see. The line. Okay,
so are you turning the lighting?
Oh, lighting.
Yeah, here is the lecture mode, production mode.
Oh, okay, wonderful. Is that okay? All right, okay. All right, so yeah, we were just in the middle of introducing the singlet ground state. And what I just want to say is that essentially all of the scattering that we'll see is going to be inelastic scattering, because we have to basically lift the system into the triplet state in order to have any magnetism at all. And so in the singlet, there's really no scattering. So all of these systems will be, in a sense, liquid-like in that they don't have any elastic scattering. However, some of the systems will be static arrangements of singlets on a lattice that don't break any lattice symmetries. And in a sense, those are pretty trivial things, and we're going to use that type of system as a way of just introducing some of the formalism and to show you what the data looks like. But what we are actually seeking is some form of a resonating system where the singlets are not static on the lattice, but are actually in some sort of dynamic quantum fluctuating state. And I'd say that that a lot of work is aimed towards realizing that resonating valence bond state, I think first introduced by Phil Anderson, who sits in the audience today. But whether we've seen it experimentally or not, I'm not completely convinced. I think it's still open for some debate, but it's certainly the goal of a lot of the research in this field. And just to remind you that we are only talking about insulating spin systems in this lecture. So there's no charge degrees of freedom apart from orbital degrees of freedom. So here's I think we're a little bit truncated for time now, but we'll see. We're going to, this is sort of the outline of the talk, a little bit of what we missed from yesterday. Then I'm going to show you what neutron scattering from a singlet ground state spin system looks like. So I've got magnetic atoms, but they form a singlet. I will do that mostly in sort of quasi one-dimensional systems. But then we're going to use frustration to try to get us towards a critical point where we may be able to realize such a resonating valence bond configuration. And this will take me through a couple of examples. We'll see how many of them we manage to do. I suspect we'll just do these three. They will show you that it's actually quite difficult experimentally to distinguish between some form of a frozen disordered spin configuration on a lattice and a truly fluctuating state of singlets on a lattice. And we'll see what the evidence is in a couple of different examples. Okay, so first, just to remind you, we were doing scattering, and so we talked about this partial differential scattering cross-section today, which is an inelastic cross-section. That's what we're measuring. We're using neutrons because of this very convenient dispersion relation between the kinetic energy of the neutron and its wave vector. The number being around 2 millivolt angstrom squared is actually key to the utility of the neutron. We've got two interactions, a nuclear interaction coming from the strong nuclear force and a dipole-dipole interaction of similar strength overall in the cross-section. And we describe the inelastic scattering in terms of these 2-point correlation functions. So these are Fourier transformed in space and time. And this dynamic correlation function is related to the nuclear interaction, and through that we will be measuring phonons and things like that. Actually, in this particular talk, we will typically try to avoid this part of the cross-section. It is in there, but we are actually more interested in looking at the magnetic part of the cross-section, which is the 2-point spin-spin correlation function. So that's the thing that we are really trying to measure in these interesting magnetic materials. Now I'd like to say a few words about that 2-point correlation function. These are just fundamental parts of statistical mechanics or quantum statistical physics. And I guess first to point out, this is what we measure. And there are various things in front that we discussed a bit yesterday, certainly are important, but fundamentally it's this entity that we try to back out from the scattering data, and it's that entity that we can talk about in terms of the mathematical developments. This is what it looks like, and it satisfies for a spin system in thermodynamic equilibrium, then we have this so-called detailed balance condition that relates the neutron energy loss processes to the neutron energy gain processes. So when we have positive energy transfer, that's a loss process where the neutron delivers energy to the system. When the neutron comes out faster than it came in, we're talking about a neutron energy gain process. And these two parts of the scattering cross-section are actually related to each other with this factor, which implies that at very low temperatures, the inelastic scattering with neutron gain becomes very weak. So I really cannot extract energy from the system which is already in its ground state. And we'll see that play out in some of these experiments.
Hi.
Yeah. Yes?
That's the formula in the last pages is relevant to the fluctuation theorem. The last equation.
Oh, in this one?
Yeah, that equation. The last one.
This one?
That's relevant to the fluctuation theorem.
Fluctuation dissipation theory?
No, fluctuation theorem.
Yeah, I'm not quite sure. I think this would probably, someone might call this a fluctuation theory. Now, I have, in order for the system to actually be in thermal equilibrium,
yeah.
I am able to derive this relationship between the two sides.
Oh, okay.
I should maybe emphasize something somewhat related to this, is that I'm never actually able to drive the spin systems out of thermal equilibrium by my scattering process.
Oh, okay.
Because I'm talking about infinitesimal fluxes, 10 to the 6 or something much, much less than Avogadro's number.
Mm-hmm.
So I can always consider the next neutron finding a system in thermal equilibrium.
Oh, okay.
And so that'll be its relation between gain, I guess this is gain and loss processes. And I would say that all of these kinds of expressions are really, really helpful for us to have available as we look at the data, because there are all sorts of experimental oddities that one has to worry about, and by knowing these kinds of relations, one can sometimes identify which parts are associated with the sample itself and which parts are some sort of background event or something. And so we're using these things all the time. And a couple more things I just want to point out. There's something called the total moment sum rule. If I integrate over both momentum and energy from a basic theorem in Fourier analysis, that relates essentially to the total scattering cross-section. And in this case, what I have over here is proportional to the total angular momentum squared of the system, because that's what's controlling the strength of the magnetic scattering. So the way I like to think about this is that the overall strength of magnetic scattering is going to be unchanged, integrating over all momentum and energy. That's some constant. And what happens as a function of temperature is that intensity is redistributing in different parts of momentum energy space. Maybe it gets collected into Bragg peaks, or maybe it goes into a singlet to triplet transition. But there's some finite kind of amount of scattering that's going to be available when I'm thinking about an insulating spin system with a certain number of spin degrees of freedom per unit, per volume unit. Okay, so that's the total moment sum rule. We also sometimes talk about the equal time correlation function, which is when I take a Fourier transform of an energy Fourier transform of the inelastic scattering that produces this entity. That may be described as a spatial Fourier transform of a snapshot of the quantum fluctuating spin configuration. And so I can extract from the wave vector dependence of this entity a equal time correlation length. And we'll see that employed in various examples. Okay, there's something called the fluctuation dissipation theorem that you're probably aware of. The way you can derive it is by starting with this time response function, expectation value of a commutator of spin operators. And you can write both the generalized stability and the dynamic correlation function in terms of that time-dependent quantity. And therefore you can relate these two to each other. And you obtain this fluctuation dissipation theorem relating the imaginary part of the generalized stability to the dynamic correlation function. And this really is the same sort of stability you would measure with a squid magnetometer, for example, except the neutrons, by measuring the scattering cross-section, we access the momentum and energy dependence of that sort of stability on the atomic length scale. So it's a really cool type of magnetometer in the sense we are working with. Here's another sum rule we use quite a bit, which is the first moment sum rule. And to derive it, we start off again with this time correlation function and its relation to the Fourier transform of the dynamic correlation function. I have this expression here. I can then look at a time derivative of the left-hand side of the equation, which gives me this expression, and a time derivative of the right-hand side expression, which gives me this one. And they must be equal to each other. And so I have this expression that relates what we call the first frequency moment of the dynamic correlation function to this equal time expectation value of a double commutator. So that's a rather kind of technical expression that you may have seen before, maybe not. You can study it a bit more yourself in the background, but what's very useful for us in looking at the scattering data, that this becomes a way of extracting relevant energy scales from inelastic scattering. So by taking this particular first moment, I get a wave vector dependent energy of the system. And I can very often relate that pretty directly to parameters of the underlying spin Hamiltonian. So it's a way, in some cases, of actually getting access to the parameters of the spin Hamiltonian without if you are in a situation where you don't have a proper theory that relates otherwise the spin Hamiltonian to the dynamic correlation function. So I can sort of experimentally obtain some pretty direct information about the spin Hamiltonian through this expression. All right, so those are various tools that we have available to us. And now let's look at the use of neutron scattering to probe these kind of singlet ground state magnets. But I'm going to start off easy examples in one dimension. And actually, the first example is extremely straightforward, which is that of a compound called copper nitrate. This is the chemical formula, and just a very rough sketch of what the spin system looks like. Something like this, and maybe don't worry about this red one right now yet, but it basically consists of antiferromagnetically interacting pairs of spin, which then are weakly coupled to each other. You could almost say that this is a zero-dimensional spin system. Each pair of spin actually will form a singlet, and they have a triplet excited state. So again, there's no elastic scattering at all from this magnetic system. However, I am able, with the neutron, to deliver sufficient energy to excite one of these singlets into its triplet state. And that will cost a certain amount of energy, which is, on average, the exchange constant for this system. So the splitting between these two is just simply going to be J. Okay, and what the data looks like is shown here. This is the energy and momentum dependence of inelastic scattering. And you see that most of the intensity sits at around half a millielectron mole or 0.45 millielectron mole, but there's some kind of sinusoidal dispersion that you see. Now the amplitude of that dispersion relates to the weak interaction that you have between these spin pairs. So that's one thing I wanted to point out. The other thing I wanted to point out is that the intensity has this funny beating pattern. I have a lot of intensity here, then it sort of goes away, and here I have no intensity at all. That actually relates to the transition matrix element for this excitation, because the spin half degrees of freedom are separated from each other. You know that these are not sitting right on top of each other. Then I end up in the scattering cross section obtaining a Fourier transform of an antiferromagnetically correlated pair of spins, and that gives me an intensity that's modulated as 1 minus cosine q dot d, d being the spacing between those two spins. So this is where this beating pattern can come from. And all of this we'll see kind of repeated when we try to go to higher dimensional spin systems and form these kinds of singlet states. We typically do carry this sinusoidal modulated intensity when we're trying to excite from a singlet to a triplet. We'll see that in 2 dimensions as well. Okay, now this was really a very simple quantum magnet. We could call it a singlet product state. The ground state is just essentially just a product of singlets. But we would like to get to a fluctuating state, so a resonating valence bond state. And this actually requires us to dispense with this neat arrangement of things where each spin knows with whom it should form its singlet. So I want to have a uniform spin chain so that each site in the lattice, and here's the physical system that realizes that. Here's a spin half degree of freedom, and it interacts with this spin half degree of freedom. It also interacts with this spin half degree of freedom, and it's unclear, whether the singlet should be formed here or whether the singlet should be formed here. And that gives rise to very interesting physics, which has been in development really since the formulation of this model of antiferromagnetically interacting spin half degrees of freedom by Hans Bethe back in the 30s, as one of the first examples, I think, of a kind of a quantum many-body system that one can actually do something exact on. So I'm not going to really talk about the Bethe-Ansatz solution and many details about this spin half system. I just want to pull out a couple of things that I'll later be able to use when we talk about the higher dimensional quantum spin systems. And the first thing is that you have a very interesting specific heat for this spin 1/2 chain. And remember that here we're talking about an insulating material. So insulators are supposed to have, at low temperatures, T to the third specific heat coming from phonons. But here we have a system where C over T versus T squared actually comes into a finite intercept. So I have sort of a Sommerfeld constant in this electrically insulating material. So that's not because I have a sort of a Fermi liquid associated with charge, but it's because I have a Luttinger liquid associated with this uniform spin 1/2 chain. So it actually does have, in a sense, a spin and Fermi points, and those give rise to this linear specific heat, a very unusual property that you can really realize in a material. You also have very unusual neutron scattering from this kind of compound, and I'm showing you the data here as a function of energy and momentum transfer. And the key feature to notice is that if you pick your wave vector transfer, and I'm going to pick, for example, let's say 0.7 here, and then I come up in energy, I see here I don't have intensity. So this is a low intensity regime. Then I obtain some intensity, and it sort of extends over a finite bandwidth of energy all the way from here to there. So I don't have sharp resolution limited modes of excitation. I actually have, even though I control momentum transfer, I actually have a whole continuum of excitations. And what that basically means is that I'm evidently not able to excite the underlying quasi-particle of this periodic spin system. Because when that happens, as illustrated here, if I'm able to create an underlying quasi-particle, then I'm going to have a sharp trajectory through momentum and energy space that reveals the dispersion relation for the underlying quasi-particle. That's the character of a single particle scattering process. So what I have instead is a continuum, and that indicates a multi-particle process, in particular for a two-particle process, even though I am controlling the overall momentum delivered to the system, by knowing the incident and scattered wave vector of the neutron. This is actually distributed to two quasi-particles. It's a two-spin scattering process. And so I'm only controlling the center of mass momentum, but not the momentum of the quasi-particles relative to the center of mass. And that means that I can actually compose a whole set of excited states with a range of energy transfer. So seeing this continuum of scattering, in a situation where I'm controlling the momentum in a system that is periodic, where I don't have disorder, that's a pretty strong indication of a situation where I'm dominated by multi-particle scattering, probably because I'm not able to create the underlying quasi-particle. Okay, so let me now, this is a little rough, but it's the picture that might be useful for, that's certainly useful for experimentalists to have in mind about the character of this